So we can use refraction, what we've learned about refraction and the bending of light as we go from one index of refraction to another, to then think about how we build lenses. And this is not going to be all that different from what we saw with spherical mirrors. It's that if you have something that comes in and it comes in along the normal, then of course, even if it's curved, if we're coming in on the normal, there's no bending in terms of Snell's law. So that's going to come on straight in. But if we hit this part, then if we look, our surface normal is sort of along that line. And so we have that. That's our angle incident. Then we're going to have a tighter angle in along the normal. And so we can imagine that if we set up a bunch of these, this is going to do the same sort of thing. And so we'll end up with some kind of focal point if we've got, this is, of course, air and glass, something like that typically. So this angle, then we get a smaller angle of refraction. And so we can get some focusing at this curved surface. And so we start to build up a lens. I mean, this would be air just coming into a big piece of glass like this. But of course, we build a lens by making it smaller and having an exit on the other side. And that actually increases the focus as well. Okay, so we can build a lens, we can start to build a lens. We'll actually build a thin lens by saying we have a side that is curved. This curvature maybe is described by a radius of R1. I don't know the curvature of that, say that's R1. And then this curve on this side is described by a radius R2, maybe it's a little further out. And we can say that the lens maker equation, the way we build lenses, is to say that 1 over f is equal to, if we're talking about a lens in air, now it changes if you're going from water to this lens. So would be n minus 1 over R1 minus R2. In this setup, the way I've drawn it, R2 is actually negative, so we'd have a positive absolute value sign here. We're not going to use this. I just want to point this out. This is what's called the lens maker equation. So this is the lens maker equation. And for those of us who wear glasses, we're actually familiar with this term. 1 over the focal length in meters is what is called a diopter. And so that's what your prescriptions are in. So if you have some value of a diopter, like 3 is your prescription, then what that means is the focal length is 1 over 3 meters. Okay, so that's what that notation is. So somehow altogether this, the R1, the R2, the index of refraction of the material, for example, this would be a glass index, whatever glass this is made out of, the certain type of glass, somewhere around 1.5 to 1.6, depending on the material, then you can actually then grind your lens to an overall focal length. And so we sort of replace this by describing it with 1 focal length. So just like our spherical mirrors, we have the same type of situation. We describe, and that focal length that I gave you in the lens maker equation, that focal length is the point at which the distance from the center, this f, right, where light coming in would then focus, and light coming in at a parallel, right, would all focus at that point. And we generally draw the focal point both on that side and on this side. And that's sort of the focal point isn't related now to the radius of curvature as much as it was by that equation that tells you the sort of an average of the two radii of curvature that give you your focal points on either side of the lens, because you can have light coming this way and focus over here, or light comes this way and focuses over here. And so this is what we call a positive lens. So this is a lens with a focal length that's greater than 0. A negative lens is going to look like this. This is a convergent lens. And what happens is light coming in parallel, right, looks like it converges from the same point. So the light coming in parallel converges then as if it came from this point. Okay, so it converges away. And this is going to do the same thing here and like this. So this is a focal point. This is one with a focal length that's given as less than 0, and this is a diverges away. This is a diverging lens, and this is a converging lens, where it actually brings all the light together. And so we're going to have the same ray diagram kinds of rules, the same rays that we had before. And so I'm going to outline those. If we have something like this, and I'm going to mark these 2 points so we know where the focal point is, and if I have an object, then I'm going to draw some rays. And these are going to feel fairly similar to the rays that we drew for the spherical mirror. So we draw parallel. So our first one is parallel to the focal point. So instead of reflecting, because this is glass, the idea is that it goes on through. So that's our first ray. So this is ray number 1. Our second one is going to be one that goes straight through the middle. Okay, strictly speaking, of course, it refracts here and refracts here, but this is the thin lens approximation, and so we can just sort of it bends a little bit, comes along and bends back, so it's like it goes on a straight line. So there's my straight. So there's our straight line that goes from the point all the way down like that. And so that's our second one, is straight through the middle. So that's like our ray that hits the middle of the mirror and bounces off at an equal angle. And then the last one is going to go through the focal point, straight through the focal point, and then it goes out parallel. Okay, and where all of these meet, again, I'm off screen here, is where we're going to have an image. And so the image is really just off screen at this point. So I'm going to inch it in so it would be like this, essentially there. And so I'll redo some of this so you can see the rays, but I wanted to point out this is the third ray. This goes through the focal point on this side, out parallel once it hits the lens. So those are our 3 rays. We'll use them and we'll look at a couple of situations. You'll see something that's fairly familiar here. This is a inverted image. This is magnified. And in this case, this is a real image because the light is actually coming through the lens and landing here, right? So we have a real image that lands somewhere. And this is the kind of lens that you have in your eye that puts an image on the back of your retina, so that that then gets carried by the optic nerve to the brain for you to translate it. Okay, so this comes in that form. Okay, so I will then draw some other examples here to show how we use these 3 ray diagrams to get a sense of what's going on. Okay, before we get to these though, I want to point out we can use the same equations. 1 over the object, as we did for the curved mirrors, 1 over the image equals 1 over the focal length. Now the sign conventions are a little different, but I think they'll make sense. This is a positive object distance. This is a positive image distance here. Image distance. Because it's on the correct side of the lens. The light's going through the lens. And then this is a positive focal length. So that's the same as this. This one is a negative focal length, this diverging lens. Okay, so we'll practice just a little bit with these ray diagrams. We're going to go off parallel. I prefer the first 2. I think they're the easiest to use. Come off parallel, go through the focal point like that. The second one is to go through straight, so that's pretty straightforward. Ooh. But the thing is, when you're going to look at this, you actually put your eye over here, right? Your eye, this is suddenly a huge eyeball here. It looks back this way, and these rays, actually, it turns out they're not going to come together, even if I keep going down this way. So I'm looking through this way, and what I'm going to see is that from my eye's point of view, these right, like went on a straight line, they together go off in this direction, and so now I'm off screen over here, and I've got, there's my image just off screen here. My image is upright, but the light is definitely not there. So this is a virtual and upright image, right? This is where my eye thinks those beams came from, but if I put a card right here, it's not going to be there. Whereas when I'm over here, if I put a card right here, I'll interrupt the light, and I will, if I put it here, it's going to be a fuzzy image of this arrow, but if I keep backing it up to the point where it's in focus, then I'll get a nice sharp image. Okay? We're going to see, oh, and then the other one would be coming through the focal point on this side, going up like that, hitting the lens, the plane of the lens, and then going off like that. So that kind of, again, if the eye captured that beam, that would be coming from back there. Okay, so the same set, this you have to be fairly careful with. So we're going to come in parallel. Our temptation is to go down to this focal point, but this is a negative lens, which means we have to work backwards. We have to say it came from, it's going to diverge, it came from this focal point. Ooh. So it came from there. Okay, so light came in like this. It's as if it came from the focal point. The one through the center stays the same. That's why it's one of my favorite ones to use, because it just looks like that. Okay, and again, if we put our eye over here, if I look over this way, these two rays look like they came from this spot right here. So now I have an image. There's my image. It's upright, but this time it's smaller. And our equation works just like we did before. Magnification equals minus the image distance over the object distance. It's the same equation as we had before. Over here, I've got an inverted image because I've got both positive numbers over here. This is a negative image on this one because it's on the wrong side. The image is not on the side where you think it should be, and so you get a magnification that's positive, which gives you upright. Same thing over here. Finally, let me draw this last one, and this is the hardest one to get. This one, you say it looks like it came from here. It's heading towards the focal point like this, and it goes out parallel, so it's the one that would be heading towards that focal point on the long side, and it comes out parallel, and then we send it backward also on the eye, so it ends up at this same point as well. My preference is to use these first two rays. Drawing a third ray, often you risk the points not actually converging when you're trying to draw these ray diagrams. So what you do after you have the ray diagrams, you can just use them to check that the numbers that you get out are what you expect, and you can start to calculate how it is that you get your images. You may have noticed, however, that glasses, at least for most people, are not structured like this or even like this. Most people have negative lenses. It depends on whether you need readers or you need to see distance. But for me, these are actually a combination. They're mostly this, so you can see they're thicker at the top and the bottom. But sometimes you can build your lens with only one side being curved. You don't have to have both sides being curved. So you can sometimes see what's called a plano convex, which would be just half of this, a flat side on one side, or plano on concave. So you could have this where it's sort of divided in half. And it still works. It's just you don't get quite as much focusing when you do that. But that's all in the lens maker's equation. In the main thing we're going to be working with are these two equations right here, which are the same as the equations for the mirror. We just have to really watch our sign convention.